lesson 1.8 is called the nth term. All right, so our learning goal today is I can find a term of a sequence directly by using an explicit formula. So just to give you a little idea here, in the past, I would give you a recursive formula. So like I'd say the first term is, I don't know, 8, and I'd give you a rule. I'd say the nth term is you take the previous term to the nth term and let's say add 5. Okay, so we'd go 8, add 5, add 5, add 5, keep going. And that's all good, but the problem is, what if I said find the 100th term? What if I said find a of 100? Okay, this recursive formula is not a good tool to use here because we basically have to count out 100 terms, which is kind of annoying. There's got to be a better way to do it. So we're going to use what's called an explicit formula today, which will allow me to just plug in the number 100 and boom, we could find that term. All right, so which one doesn't belong? Try to come up with a reason for all of them. Pause the video and see if you can come up with a reason for one of them or all four of them. All right, so the first one, my reason for the first one, I'm going to say it doesn't belong. I'm going to say this is the only expression that uses all addition. Okay. Now, I do want to point out here, since I have repeated addition, I could change this into 5 plus, looks like I have 1, 2, 3, 4, 5, 6 twos. I could say 5 plus 6 times 2, and that would give me the same number. These are the same exact expression. This way here is a little more condensed using multiplication. Okay, come down here. I'm going to say this is the only expression that uses both addition and multiplication. Okay. C, maybe say only expression with an exponent. And maybe this one I'm going to say only expression that uses only or all multiplication. Now, some of you might argue, and I would probably argue too, that C uses multiplication because technically these two are actually the same thing. They're equal. Because if 5 times 2 to the 6, 2 to the 6 is really 2 times 2 times 2, 6 times. Okay, and that happens to coincidentally be the same thing here as D. So, this is called expanded form. And then this is called exponent form. So same expression, C and D are actually equal, but just getting us used to writing expressions differently. Okay, so let's take a minute, pause the video, read this problem. All right, basically what's happening is Claire's taking a piece of paper that has a width of 8 inches. I got a little picture here and I'm gonna label it W equals 8. And a length of 8. I actually did that wrong. Let me erase that. Length equals 8. And the width is 10. So, all right. And basically, she's going to start cutting it half and then cutting it half again and again. So remember, area of a rectangle. Area of a rectangle is length times width. So the area of this whole thing starts out at 80. Okay. So instead of writing a recursive definition, Claire writes this definition here. C of n equals 80 times 1/2 to the n. So it's real important to make sure you realize what C is and what n is. So C is the area. Okay, so C of n here, this is the area in square inches of the paper after n cuts. Okay, so n is the number of cuts. Explain where the different terms in her expression come from. Okay, so see it. So 80 times 1/2 to the n power. So I think 80 is going to be our initial area. All right. Um, so you're basically timesing it by 1/2 over and over and over again because you start out with 80. If you cut it in half, you're at 40. Cut it in half again, you're at 20. Keep cutting it in half. You keep, basically what happens is you get times 1/2, and you basically get repeated multiplication there. So if I wanted to find, after two cuts, it's like I start out at 80 and I cut it once and I cut it once. So it's like I times it by 1/2 twice. So it'd be like kind of like I plugged in here 2 instead of writing 80 times 1/2 times 1/2. I can condense that into 80 times 1/2 to the second. And then same thing here. If I want to do it 3 times, I want to do 3 cuts, instead of writing times 1/2 times 1/2 times 1/2, I could just change that to the third power. Okay, so um, as I look at that, I would say the n comes, or I'd say the 1/2 to the n. I would say 1/2 to the n, and I'm going to erase all this here that I had. Say this. Let's get a highlighter here. This 80 is our initial area. The 1/2 to the n comes from repeated multiplication of 1/2. So that. All right. And then the C of n can obviously be the area that remains. All right, so those are the different pieces of the formula there. Kind of neat. So now if I want to find like after the 50th cut, I could just plug in 50 right here for n. All right, approximately what is the area of the paper after 10 cuts? Okay, awesome. So before we would have to count out, like kind of like I was doing, I'd have to count out 10 terms, but now I can just say, oh, okay, C of 10 equals 80 times 1/2 to the 10th. Okay, so you're going to take your calculator there, make sure use your calculator, make sure you type it in, and make sure you know how to type this in. Use parentheses there for that 1/2 to the 10th times 80. And I don't even think that my calculator will give me a fraction. Oh yeah, it will. It's actually 5 out of 64. 5/64 is my area. And that's square inches, I believe. All right. As a decimal, it was 0.0781 square inches. I prefer the 5 over 64 because this I had to round. It actually was 0.125. That might have been exact there at the 25. But yeah, fractions are always better than decimals because they're more exact. All right. So Kieran takes a piece of paper with a length of 8 inches and a width of 10. Oh, I turned it this time. My width is 10. My length is 8. The longer side is the 10. And this time he cuts away 1 inch. So here's what I'm going to do. I'm going to kind of do a dotted line here. It's kind of like, whoops. Kind of like that. He cuts away 1 inch each time. So it's like he removes that piece of paper, that little strip there. So he starts out with 80. He cuts it once. He's going to be down to, let's see here, he's going to be down to 78, right? Because he cut off this little strip here. And what was the area of this strip? Well, it was 1 times 8. So it's like he subtracted 8 from here. All right, and then he's going to do another one where he cuts another 1 inch from here. Whoops, I wanted that to be a dotted line. Oh well, it didn't work. So he cuts another, and this is the same area. It's 8 times 1, so he's removing another 8. So why am I at 64? Oh, I don't know why I said 78. I'm silly. This shouldn't have been 78. 80 minus 8 is 72. Whoops. And then if I minus 8 again, minus 8 again, that's how I get to the 64. And then I keep minusing 8. So this is going to be 56, 48, 40. Okay, so there's my table. So Kieran says after 6 cuts, the square inches is 80 minus 8 times 6. All right, explain where the different terms in his expression come from. Okay, so K of n equals 80 minus 8 times 6. So this is my area remaining. Eighty is my initial area. The 8 is the area removed on each cut. And the 6 would be 6 cuts. Okay, write a definition for K of n that's not recursive. So I'm going to kind of use, or I guess this shouldn't have been K of n. This should have been K of 6, technically, because we knew how many cuts we made. So if I wanted K of n, basically we're just going to use the same formula, but instead of 6 there, it's n. Okay. So eventually, after 8 cuts, he's not going to have any paper remaining because after 10 cuts, he's not going to have any paper remaining because 8 times 10 is 80. So 80 minus 80 would give you 0. So he cannot cut it any more than 10 times. All right. So which is larger, K of 6 or C of 6? So C of n was 80 times 1/2 to the nth power. So if I wanted to find C of 6, it's 80 times 1/2 to the 6th. And actually, I already did that. Right, I did. No, I didn't do that. I did that after 10 cuts. So I'm going to type that in my calculator. 80 times 1/2 to the 6th. So I get 1.25. Whoops. And that's square inches remaining. K of n was 80 minus 8 times n. So 6 cuts. Actually, that's what we just did. We actually found that. No, we didn't find it. I'll go ahead and find it. K of 6. So it's going to be 80 minus 48 gives me 32. So obviously K of 6 is much larger than C of 6 in this case, okay? All right. A Sierpinski triangle can be created by starting with an equilateral triangle right here and breaking the triangle to 4 congruent equilateral triangles and then removing the middle triangle, starting from a single black equilateral triangle. Let S be the number of black triangles in step n. Define step n recursively. Okay, so we have 1, we have 3, we have 9, and then if I count the number of black triangles here, it looks like 27. Okay, so define it recursively. So define the nth term, S of n, you take the previous term, and it looks like you times it by 3. Okay, we would need to know the first term. Okay, and then we would say n is greater than or equal to 2. Okay. So the only other thing here is, I guess, depending on what you call step 1, um, some people might call this step 1 because you're starting with this triangle. So some people might call this step 0. Some people might call this 1, 2, and 3. All right, because technically you haven't divided it yet. So some people might say S of 1 might equal 3. Okay, so it's a little tricky there. It's, I guess, depending on how it's worded. This one isn't very clear how it's worded. So for what we're doing, we'll say that this is like step 0 and this is step 1. We'll say S of step 1 is 3 because he technically hasn't divided any triangles yet. So he starts with this and then he divides it. So, all right, number 2, Andre and Lynn are asked to write an equation for S that isn't recursive. Andre writes S of n equals 3 to the n. Lynn writes S of n equals 3 to the n minus 1. Whose equation do you think is correct? Explain or show your reasoning. So, all right, if I use the steps here like I had, let's go with Andre first. So 3 to the 0 should give me 1, which it is. 3 to the 1 for step 1 should be 3. These both work. Step 2 would be 9. That works. And then step 3, 3 cubed is 27. So Andre's works. Okay. Now Lynn, here's the thing with Lynn. Lynn's is going to work if we numbered it the way that we did originally. So if I called this step 1, this step 2, step 3, step 4, Lynn's is going to work also because it's like 3 to the step 1, 1 minus 1. 3 to 0, which is 1. And then we plug in 2. 2 minus 1 is 3 to the first, which is 3, which is what we have here. So I guess it just kind of depends how you number it. And this problem is a little unclear on what is step 1 and what is step 0 and things like that. So they could both be right. Okay. So I'm going to say both are right, depending on if you start with step 0 or step 1. So both can. Right, so it really just depends on which one you start with. All right, so our synthesis. Here's C, here's E. Pick one of the sequence of any equation for the nth term. So we want what I call an explicit formula. Let's maybe do both. Let's do an explicit and recursive. So let's see here. This one is geometric because it's times 2. So first term, I'm going to go the old way. I'm going to start with the recursive. C of 1 equals 1. And to find the nth term, I take the previous term and I times it by 2. And there we go. That's my recursive formula. If I wanted an explicit, You start with 1, okay, and then you times it by 2 to the n minus 1 power. Because this is the first term, second term, third term, fourth term, fifth term. So to go from here, I'm timesing it by 2 one time. Okay, so I don't want to plug in 2 here. I don't if I just did 2 to the n, that would be like I'm timesing it by 2 twice. But like to get this second term, I only want to times it by 2 once. It's 1 less than the term number. Okay. So that would be my explicit formula there. Now this one is arithmetic. It's minus 7 every time. So if I wanted to go with my recursive, start out with the first term, e of 1 equals 20. And then if I want to find the nth term, I take the term before it, and I minus 7. And we're only going to count up from 1, so n has to be greater than or equal to 2. Now if I want to find my explicit, I'm going to do repeated subtraction, so that's going to turn into multiplication. So if I wanted to find the nth term, I start with 20, and I'm going to subtract 7 n times, okay? Well, actually, that wouldn't work, because if you think here, to get to the second term, I really only want to subtract 1 7. I don't want to subtract 2, because this is term 2, term 1, term 2, term 3. So it's actually going to be 1 less. So it's going to be 20 times, or 20 minus 7, then minus 1. So let's test this out. Let's just test it out. Let's see if the second term is 20 minus 7 times 2 minus 1. So this is 20 minus 7 times 1. 20 minus 7 is 13. Does that work? Is the second term 13? Yes. Okay, so that would be my formula here. Let me clean that up a little bit. All right. So there's my explicit formulas. Okay. All right. Last thing, cool down. Here's my sequence. They start with the 0 term, and they give us our recursive definition. So you're going to add 0.5. So that's going to be negative 2.5, negative 2, negative 1.5, and so forth. Diego writes an equation for the nth term. It is f of n equals negative 3 plus 0.5 to the n. Is he correct? Explain how you know. All right, well, let's just see here. This is term 0, because we start with the 0 term. 1, 2, 3. Let's just test it out. What would f of 1 be? F of 1 here be negative 3 times plus 0.5 times 1. That works. What would f of 2 be? I'll use my formula here. I just plug in 2 right there. Negative 2, that works. F of 3. Looks like it works. F of 3, negative, yeah, that works. So I think he's right. And I would explain how I know with my work right here. I tested the first 3 terms. Or I guess I tested term 1, 2, and 3. All right. All right. Hope you enjoyed the lesson. Make sure you do your homework for lesson 1.8.